Ooh, this is a lecture on evolution of Earth and the solar system. This lecture will provide an overview of how Earth and our solar system formed, the structure of Earth, and some of the major topographic features on Earth's surface. Our SLOs include briefly describing how the solar system formed, being able to list the 5 physical layers of Earth in their correct order and compare and contrast the asthenosphere and lithosphere, and describing the major topographic features of the continents and seafloor. Keep in mind, this is not all that you need to know, but these are the big ideas. Let's talk about the nebular theory and the formation of our solar system. The nebular theory is an explanation of how our solar system formed based on observations about how other solar systems form. A nebula is a large mass of very small solid and gas particles. Nebulas will collapse due to their gravitational attraction between particles. This could be perhaps initiated by a shock wave from an exploding star, also called a supernova. As the material becomes more and more concentrated, it heats up, with the greatest concentration of material condensing and heating enough to eventually become a star. The leftover stuff will continue to collide and clump together through a process called accretion. This forms planets, moons, comets, and asteroids, and the other stuff that you find in a solar system. So in this photograph here to the right, we have 2 nebulae, and it's observations like this that have allowed us to formulate the nebular theory. We see that in these nebula, there are stars forming, and associated with some of those stars, planets. And we see that these solar systems are forming at different stages throughout our galaxy. So just putting the observations together, we've developed what we now call the nebular theory. Let's look at this animation from your textbook. Let's make sure I'm sharing the screen here. And this should work.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the main points behind the nebular theory for the origin of the Earth, the Sun, and the whole darn solar system. So the nebular theory is basically an explanation for where our solar system came from, and it's based on observations of other bodies elsewhere in the universe. But the idea is that a large cloud of space, dust, and gas condensed into our solar system. So this cloud of dust and gas condensed initially because the little particles were attracted to one another. Gravity pulled the matter together into a denser sort of disk, and that disk compacted into less and less volume. Some of the matter in the middle of that spinning disk actually got so closely packed together that the individual atoms began to merge, and that's thermonuclear fusion, and that's the birth of our sun. So the sun is where most of the matter in the solar system is concentrated, but there is some matter that's distributed in a broad ring surrounding the sun. That ring became clumpier and clumpier over time, where material again sort of collided, little particles collided, and material became more and more concentrated in a lesser and lesser number of larger and larger objects. And that process, something like 4.5, 4.6 billion years later, has resulted in a star that's surrounded by 8 classical planets and a bunch of smaller objects, including the asteroid belt, comets, dwarf planets, and so on. So that's the basic idea behind the nebular theory. It's basically an explanation for where the solar system came from. This is an image of Jupiter in 1994, and that big red dot that you see in the middle there is a spot where a comet Shoemaker-Levy 9, collided with Jupiter. How is this event representative of the ideas behind the nebular theory? If you answered that this is basically one more event in that sequence of concentrating the matter of the initial nebula into a smaller and smaller number of larger and larger objects, then you're right. Basically, this took, a little comet that was out there in the solar system and merged the mass of that comet with the mass of Jupiter. So on the day this impact occurred, the solar system lost one more object and Jupiter got a little bit bigger. Collisions like this happen all the time, but they happen far less frequently in the modern day than they did early on in the history of the solar system.
So that's a nice summary of how our planets grew over time from the origins of our solar system 4.6 billion years ago to where we are at today. That short animated video is also an example of the smart figures from your text, and I encourage you to use those. They, I think, will help you better understand the material that we will cover this semester. So this illustration here is intended to help us conceptualize the vast sizes of objects in our solar system and the vast distances between them. So we start with Earth and its circumference of 40,000 kilometers or about 25,000 miles. It would take a jet plane, so a passenger jet that perhaps you've flown in, about 40 hours to fly all the way around the Earth to circumvent the planet. Look over here to the right, we see Earth, which we've just discussed. It would take about 40 hours to fly all the way around the Earth. It's big for us. It's a big planet. But compared to the Sun, the Earth is tiny. In fact, the Sun contains 99.86% of all the mass in the solar system, which is just incredible. It's almost everything. Yet the planets are still quite large compared to us. The circumference of the Sun is 109 times that of Earth, so way, way bigger. If you were in that same jet plane, instead of it taking you 40 hours to fly around the Sun, it would take you 182 days to fly all the way around the Sun. In terms of this distance from Earth to the Sun, it is 150 million kilometers or 93 million miles. We refer to this as one astronomical unit, and we use it as our reference distance when we're comparing the distance between objects in space. I'd like to break down the math that was used to solve the first problem from the previous slide. How long would it take to travel around the Earth in a jet plane? When we're talking about how long and distances and speeds, we are talking about a rate problem. Rate equals distance divided by time. We should all be familiar with rates because we drive or walk or pedal past them all the time. Those are the speed limit signs that we see. 40 miles per hour, for example, would be a rate, distance divided by time. So I'm going to break down the math from that problem on the previous slide. How long would it take to travel around the Earth in a jet plane? In order to solve this, we need to consider that we are dealing with a rate problem. And as you might remember, rate equals distance divided by time. And in this problem, we are asked to solve for time. How long would it take? So we need to rearrange our equation here. And I'm going to do that by trying to get time by itself. First step will be to get the time out of the denominator position here. And I'm going to do that by multiplying by time. And whatever I do to one side, I have to do that to the other. The times will cancel out there. Let's rewrite the equation over here. It's now time times rate equals distance. I still don't have time by itself, so now what I'm going to do is divide to get the rate away from the time. So divide by r here, and whatever I do to one side of the equation, I have to do it to the other. The rates will cancel out there. I'm going to rewrite the equation again. Now I have time equals distance over rate. So that's how I need it set up. So now I can plug in what was given to us. Going back to the previous slide, what's been given is a distance of 40,000 kilometers. And a rate of 1,000 kilometers per hour. My kilometers will cancel out, and then I'll divide 1,000 into 40,000. But before I do that, I'm going to cancel out the zeros to make it easier to do. Let's rewrite it down here. Time equals 40 over 1, with our only units being hours. And of course, 40 divided by 1, it would be 40. So time equals 40 hours, which agrees with what is given to us in the illustration. All right, let's take a closer look at that figure from a few slides ago. And here we're now looking at how long it would take to go from Earth to the sun in the same jet plane. So we know flying around the sun is going to take 182 days. To fly from Earth to the sun would take 17 years at that same rate. So incredibly far away. Over here on the left, you see these questions. What is the approximate distance between the sun and Neptune? How long would it take a jet plane traveling at 1,000 kilometers per hour to go from Earth to Neptune? So these two problems you are going to solve, perhaps using my tutorial from a couple slides back as a guide. Come up with answers, and then you will input your answers in this assignment in Canvas called Solar System Calculations. And again, those are based on these questions here. A little bit more about this illustration. This shows the planets at their relative size to one another and relative to the size of the sun, to help put things in perspective. It also shows their relative spacing, although of course they're actually this close to each other. This makes it look like the sun is right there, but remember, it would take 17 years to reach the sun. It's 93 million miles away. We see that the terrestrial planets are pretty even in their spacing. And then we get these big jumps in space when we get out to the Jovian or gas giant planets. Okay, let's move on. Earth's structure. So let's talk about the Earth in particular here. We'll start a discussion of our solar system with Earth and its internal structure, which formed through the process of accretion that was mentioned earlier. To review, accretion is the accumulation of particles into more massive objects by gravitational attraction. As matter coalesces to form planets, the heaviest materials will sink to the center, while the lightest materials will rise towards the top. This causes planets to have layered structures. So the densest material is in the middle, and then we get progressively less dense stuff as we get towards the Earth's surface. This layering can be defined two ways, either by chemical composition or by physical properties. Chemical composition is just differences in what the stuff is made of, and physical properties is differences in how the material behaves. In terms of chemical composition, the core is made up of different material than the mantle, which is made up of different material than the crust. It's all rock, but the rock is different in composition. Most iron and nickel rich here, a lot of iron and magnesium in the mantle, and then a lot of silica in the crust, the lightest stuff. In terms of physical properties, again, this is how the material behaves. It's its state of matter. The core is solid, the outer core is liquid. The lower mantle is solid. The upper mantle, which is zoomed in over here, is solid, but not a complete solid. It's mobile. Think of it being kind of the consistency of jello. So this fourth layer from the Earth's center, the asthenosphere, is hot enough that it's not a true solid. This is very important for plate tectonics, which we will discuss later. The uppermost layer in terms of physical properties is the lithosphere, which includes the crusts and the uppermost part of the mantle. In terms of what we need to know for our class, we're going to focus on the lithosphere and asthenosphere. The lithosphere is the solid outermost layer of the Earth. We live on top of the lithosphere. You guys are walking on top of the lithosphere every day. So the top half of the lithosphere is the crust, both the ocean and continental crust. The lower half is the uppermost mantle. The lithosphere is this solid shell covering the Earth, but it's not just one continuous piece, and instead it is broken up into individual pieces called tectonic plates. Think of a hard-boiled egg where the shell has been cracked into several large pieces. These sit on top of the asthenosphere, which is in a way like the white of a hard-boiled egg, semi-solid, squishy, like jello. And because of the heat, it is slowly flowing. And more on these guys later. So on Earth's surface, we have oceans and continents. Oceans cover about 75% of the Earth's surface. Oceans fill in the lowest elevations of Earth's surface, the ocean basins. These regions sit lower because they are made of denser, heavier rock, which is pulled closer to Earth's core by gravity. Two main topographic features of the ocean basins are the mid-ocean ridge system, which is this long, curving, continuous mountain range at the bottom of the ocean. It spans the ocean basins like the seam on a baseball. So imagine a baseball or softball with that stitching that traces all over the top of the ball. That's like the mid-ocean ridge system for Earth. So this sits higher above the surrounding ocean floor. In contrast, The deepest places in the ocean are called the deep ocean trenches, and those exist close to the continents, right at the edge or margins of the ocean basins. And again, we'll get into those in more detail later as well. As far as the continents go, the continents have mountains and shield areas as their primary features. Obviously, the continents are sitting higher than the ocean basins, and this again is a consequence of density. The continents are made of less dense rock, so they sit higher, or in a way you could think of them floating in the same way that ice cubes float just above the water surface in a glass of water. The continents are, in a way, doing the same above the ocean basins. We see the young mountain belts of the continents stretching from the tip of South America through Central America and into Northern America, all along the western coasts, and then around the Pacific Ocean and down the eastern side of Asia, down through Indonesia and the Philippines, down to Australia. Then we have another major young mountain range stretching from Eastern Asia across Europe. And this includes the biggest mountain range on Earth, the Himalayas. There's also older mountain ranges that are scattered about on the continent in different places. The shields and stable platforms make up the other major component of the continents. Young versus old mountains. So young mountains are those that are tectonically active. They are currently growing and getting taller. The constructive forces that are building these mountains up are working faster than the destructive geologic forces can wear them down. So they grow taller and they have commonly this jagged appearance. They look young. On the other hand, older mountains are those that have stopped growing. There's no longer any tectonic uplift. And instead, the destructive geologic forces are wearing them down further and further and further over the course of tens, hundreds of millions of years. So they look much more subdued than do the young mountains. Shields and stable platforms. Shields represent the core of the continents. This is the original part of all the continents. If we go back to our illustration here, shield, 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 shield. All the continents have their own shield. Again, representing the ancient core of the continents from when the continents first formed, going back over 4 billion years ago. Covering the shields are younger sedimentary rocks, and in these areas we call that the stable platform. In both cases, they are not tectonically active. So these areas have been worn flat or nearly flat. Think of the Great Plains in North America as a good example of this. We finish this lecture with a mini quiz. I will be adding these to some of our lectures, maybe most of our lectures, and they are there to help you review what's been covered and help you prepare for the major quiz, which will be at the end of the module. So these quiz questions will be answered in Canvas. Look for the assignment mini quiz 1. So that is the end of this lecture.